First of all, we're actually very happy to have partnered with Nimbix, and I'm supporting our hardware on the cloud. This is going to be more of a hardware-centric talk compared to the application ones we've seen. So hopefully I don't put everybody to sleep. So I'm going to talk a little bit about how we see GPUs and CPUs compared to an FPGA. How do we program FPGAs? As we saw this morning, one of the main issues is programming the thing. Doesn't matter how good it is if it takes 6 months. Some of the cloud workloads that we've seen are good for FPGAs. We believe we can accelerate everything, but in reality, there's specific class of workloads where we are good at. There are workloads where CPUs are great at, and there are workloads where GPUs are really good at. So we're going to go through an optimization case study, and then how you can get started with using FPGAs on the Nimbix cloud. So the way we see CPUs and GPUs, so it's a fixed architecture machine. It runs at a high clock rate. It may have some acceleration cores built in, like the latest Intel processors, and it's a function, instruction, fetch, decode. So the compiler is not easy, but it's magnitudes simpler than building an FPGA compiler. So, and what you can achieve is limited by your toolchain and your coding style. So, since I'm more of a hardware engineer, I have hardware-based analogies, not HAL 2000. So the way we see a CPU and a GPU is more like a car. Depending on how much money you want to spend is what you can get. Now, the key thing about all of these is that the basic operation is the same. They all drive, and they all consume fuel. And nobody has to teach you how to drive this car if you learn how to drive on this one. You may not be the best at it, but you'll be able to get from point A to point B. Now, with an FPGA, as was mentioned earlier this morning, it's a tiled architecture as a blank slate. You can think of it as a box of Legos. You can build whatever you want. We have memories inside of the fabric, we have multipliers, DSP units, and we have lookup tables. And we also have very flexible I/O interconnect. So as compared to a CPU or GPU, where you need daughter boards to bring your data in, we can have your video stream, your Twitter feed go directly into the FPGA chip and do processing, which gives us very low latency. So in a little bit more detail, all of our FPGAs, whether they're Xilinx, Altera, or whoever, are going to have a similar kind of architecture where we have the same types of resources replicated around the fabric. And every time you build your function, you're building a specific connection of those logic elements. And those logic elements are going to have multiplier units, multiply accumulates, as well as distributed memories. Now, if that wasn't enough to make FPGAs difficult, every time we come up with a new family, we tweak these to make them more power efficient and faster, or change the size, which changes how they get programmed, which makes all your code from the previous version unusable. So with an FPGA, if you know what you're doing, you could build that, or you could get the Batmobile, or you could get the Millennium Falcon. The FPGA allows you to do that. The problem is, when you get it out of the box, it looks like that. We don't have the Lego instructions to tell you step by step how to get to the Millennium Falcon. We just give you all the pieces. We give you tools, and we wish you good luck. So this is what we're trying to change, and this is what we're trying to change with our partnership with Nimbix. So in terms of programming FPGAs, we'll look at the CPU model as the standard de facto programming experience users want, in that you have your code written in some language, C and C++. You have a compiler, a profile, and a debugger, and it targets the processor. You do not have to be an expert in the architecture of that processor to get something to work. So with the FPGA, we're going with a processor offload model, where we're still working with a processor, and we're identifying that you have functions in your code that need acceleration. So not all of your code needs to run as fast as possible, but some critical portions do. And for that, we created our STXL compiler toolchain, which I'll talk about, which also provides a compiler, a profiler, and debugger. And allows you to take your kernel code written in C, C++, or Opencl, or to use pre-canned libraries to get your work done on the FPGA card. At least that's the hope. Now, to get to this point, we're a hardware company. So we are learning about software flows. We're learning about what it means to be on the cloud. So where we started, and where all of our users have started, is there's a processor somewhere in your system, but the rest of your design is all hardware design. So if you're a hardware engineer, the FPGA lets you build whatever you want without having to pay for an ASIC. We recognize that this market on its own, while it's makes us a lot of money, is not enough. And we need to expand to new classes of users, mainly software programmers, application developers. So the first thing we did was buy a company that specializes in C2 gates compilers. So we could accelerate at least your creation of your IP block that's going to be your function. But this was still a mixed design model, because how you talk from the processor to that accelerator was still hardware design. We expected our end user to still understand the concepts of PCI Express, DMAs, interconnects, and everything else that makes FPGA design interesting or difficult, depending on your definition. So what we're moving to right now is with SCXL, a single language environment where you can express your entire application or the part of the application you want to run on the FPGA card in one concise language, so C, C++, or Opencl. So it's the same tool chain. It doesn't require you to understand the underlying architecture besides a few overall concepts. So the main point of SDXL is that we'll take a user application code, and it may be a subset of the application that will be divided into a host code and a kernel code. The reason we chose Opencl is that it gives us a clear definition of what it means to talk to an accelerator, a clear definition of what a platform means, and how to execute jobs on an accelerator. So the host code is based on Opencl APIs. It does all your scheduling and coordination of your job. And your kernel is either Opencl C kernel language, C, C++ code, or libraries that you've gotten from one of our partners. SCXL will compile your program into executables for the processor and also into a binary that's going to go on the FPGA card. And at the same time, we provide an Opencl library that links the two together. So this will interpret your API calls from your host processor down to the FPGA card without having to understand the specifics of the physical link or the specifics of the processor. So one thing to keep in mind is that when we're using SDXL, we are creating hardware, even though the entry language is C or C++, which means this takes time. Whereas in a GPU or CPU, you're compiling to a well-known fixed architecture, where you're only generating machine code. Here you're creating logic, and you're creating connections of that logic based on your custom algorithm. Therefore, we cannot compile in the same time that you can do for a GPU or CPU. So SCXL has optimization phases that allow you to get a more software-friendly developer experience and accelerate your algorithm before trying to go to the board. So we've identified SCXL into phases. The first one is what we call CPU emulation, which is we're not actually going for any acceleration. We're just trying to make sure that the code that you're feeding into the tool works and that the results you're expecting out of that code is correct. So the compiler is, we've been verifying it over the past 10 years that whatever you wrote in your code, we will create functionally equivalent hardware, but we have no way of verifying that your original code was correct. So that's left to the user. Afterwards, we have to estimate if what you want to run on the FPGA will actually fit. So unlike a CPU or GPU, where the constraint is not how many lines of code you have, it's your memory bottlenecks, it's your performance. In an FPGA, it's also how many resources you have. So although we produce a wide range of FPGA fabrics, depending on different applications, not all fabrics are good for acceleration because of the size that's available to you. So that's part of our estimation phase. And then we go into this phase where we look at the performance of this accelerator on the hardware. So before you get onto the hardware, you will be able to do a very accurate thread level simulation of your entire system, so you can verify that your kernels are working how you expect them to work. And finally, we compile to the board and run on the FPGA. So the reason why we have these three phases is because of execution times of the tools. So for example, compiling any application and running it on a processor just to verify functional correctness, compilation is in the order of seconds. Compiling it to verify performance in an emulation model is in the order of tens of minutes. Compiling it to run on the board, it's an hour at least. So the way we are accelerating design turns is by giving you steps before trying to get to the board that will allow you to test that your application is behaving as you expected before you burn that hour and go to lunch or go to sleep. So as part of providing a complete tool chain, and this is where we are still learning and growing, we're developing our ecosystem. So from Xilinx, you will get the SDXL compiler environment, which has a compiler, debugger, profiler, and libraries. This will work on x86 or a power server for our host code, and your accelerators will be on partner boards. So we have partner boards from Alpha Data, which are installed currently at Nimbix, Pico Computing, and for DSP. We also have an ecosystem of application developers that are ready to help you optimize your application, as well as library partners. And the latest addition we've had to our ecosystem is our cloud provider, which we're very happy to have Nimbix as our first cloud provider for Xilinx FPGAs. So, okay, we have a tool chain, we have a board, we have a cloud provider. What are the workloads that actually work on this thing? So we identified 4 classes of workloads. First one is video image processing, security, deep learning, and genomics. For this talk, I'm going to focus on video and image processing and deep learning, which have the most user base so far. So for video processing, one of the biggest consumers is YouTube, Netflix, HBO. Everybody's starting to get video on demand streaming. And this requires constant transcoding to happen on the web so that you can get your video in the right format for your device. Now, if we compare the latest H.265 or HEVC encoder compared to H.264, it's about 10 times more complex. It's targeted at resolutions that are 4K, 2K, so all the nice shiny TVs. And it has more color depth. So it is computationally more expensive than the previous encoding standard. And current deployments of this focus on x86 servers. And just to give you a ballpark, to transcode a video, 4K video, requires 11 i7 octa-core CPUs to get this going, and this is not real time. This is 11 processors to get 17 frames a second. So several hours to transcode your video. So, okay, this looks like a good target for an FPGA, and there are multiple phases of transcoding that could be targeted to the FPGA. So what makes sense? One thing to keep in mind as offloading to either an FPGA or GPU is your compute time should be significantly higher than your transfer time of data. So in this case, we've measured it out in milliseconds for different phases of HEVC, and we see that the most valuable part to accelerate is probably going to be this middle, the decode, the video processing, and then the encoding again. So this maps well to an FPGA fabric because it is bitwise pixel operations. All the data can be constrained within the FPGA, as we'll see in our example. And it reduces the amount of data that you're sending over the bus between the processor and the accelerator. But just having an IP block that does this is not enough. As we saw in the presentation earlier this morning, Core Genomics was using FPGAs, and they worked well for a certain amount of time. But afterwards, the algorithms got ahead, and realistically, keeping up with the FPGA didn't make sense. So just having an IP core or having this functionality on the FPGA doesn't make sense if the end application can't use it. Which brings us to layering this accelerator in a way that is transparent to the end user application. So if I look at using FFmpeg, which is quite popular in doing transcoding workloads, FFmpeg has an Opencl framework underneath because it's leveraging multiple CPUs and it's leveraging GPUs. So we can piggyback on top of the same thing and have an accelerator card that will plug in as an FFmpeg plugin, and your end user of FFmpeg or the applications you built on top of it does not need to know that there's an FPGA in there, does not need to know that you spent money on an FPGA or that you programmed one. It just works. And because of the partial reconfiguration technology that is included into our FPGAs, this board is not a single application board. It can be doing a transcoding workload for the next 3 hours, and afterwards it can switch to a machine learning application, or image resizing, or finding cat videos on YouTube, whichever is the workload that you need to process. Now, okay, this has significant higher development burden, so what is the main advantage of an FPGA? Besides latency, it's power. So for this workload that required 11 i7 CPUs, our latest devices, which is the Kintex UltraScale 115, can do the same transcoding workload in one FPGA board. This gives you 4K, 2K video encoding at less than 60 watts, running at 30 frames a second. So it's double the performance, significantly less power consumption, and this allows you to get higher density and higher throughput for your overall implementation. So let's look at deep learning and machine learning. There is a lot of talk about machine learning, the applications. We saw it in all the presentations so far. So who's actually using FPGAs for machine learning? One of them is Baidu. Baidu is one of the Chinese largest search engine providers, and they're using it to classify images. Now, machine learning has two stages. There's a training stage where you're trying to find out those coefficients that will give you the right prediction and the right model. In that stage of machine learning, the FPGA does not have a spot. On those places, you need the highest resolution of your coefficients, and training is either happening on CPUs or GPUs where you need the maximum floating point performance. Now, for the prediction stage, where you just want to find those cat videos as fast as you can, and if it's a white cat or a black cat or a purple cat, doesn't make a difference as long as it's a cat, you can use FPGAs for the low latency processing. Also, because you started with high resolution coefficients, losing some of that precision on the FPGA fabric is not going to negatively impact your classification performance to a point where it's noticeable. So Baidu did this example comparing CPUs, GPUs, and FPGAs to validate their investment in GPU fabrics. So as we all know, when deploying new hardware, CPUs are the easiest. GPUs, depending on your deployment, can be thought of as exotic. FPGAs don't figure in most people's minds, especially DevOps or IT teams. So this kind of performance gain is one of the justifications for putting an FPGA inside of a data center. The other example we have is Microsoft Bing. So Microsoft decided that for their Bing search, they wanted to put an FPGA, but one of the requirements of this FPGA is that it needed to be passively cooled. It needed to fit on this small piece of the server that was still empty, and did not have to require any hardware changes on their side. So this means that this part needs to work at almost 70 degrees Celsius, be able to perform continuously. And they have a document parser that's doing web searches. So in terms of what they're doing, when comparing with this server with the accelerator compared to just a server with only Intel CPUs, they get about a 30% latency reduction. They also get a 30% less cost because they're reducing the number of boxes to hit this performance target. So, and they're also consuming 25% less power, which overall reduces their overall cost of delivering your search engine results. So these two are companies that are leading web searches worldwide, and they are starting to deploy FPGAs at a massive scale because of the cost reductions. Now, both in the Baidu and the Microsoft case, they did a traditional FPGA design. They did not use any software automation. They didn't use the tools. But they're the exception of what we expect customers should be doing with these devices. They are at the forefront of improving that an FPGA accelerator works. We are now showing that an FPGA accelerator can be used for different workloads without requiring the end user to be the size of either of these companies. So in terms of what we can do against other workloads, Smith-Waterman and SHA-1 encryption hashing algorithms are also very good on FPGA fabrics because they're about moving bits around, bashing bits, XOR shifts, things that the FPGA fabric can just build naturally. So let's look at what happens when you try to optimize the workload on the FPGA. I'm going to use a case study from one of our partners who did a machine learning application. So their goal was to build a vehicle classifier. So take a sample image and be able to detect if there's a vehicle, something with wheels in that image or not. Bicycle, truck, car, whatever. So what they did, they started with CUDA, and they used a GPU to do the training. So they got their high fidelity coefficients out of the GPU. And then they decided that to make this scalable and be able to sell their application, they needed to have low latency and they needed low power so they could replicate it. And so they decided to try out an FPGA. And they took their same code, which is taking 96 by 96 color images, and did a comparison. Just as a disclaimer, they also already had this application running on a CPU and they were selling it on the CPU. So this was just a proof point to see if they could use an FPGA. So the hardware they were using is the same processor on both systems. The only difference is the training system uses an NVIDIA Tesla card, and the prediction hardware is using Xilinx Vertex 7 based FPGA board. So next slide shows you what happens when you just take code that was for a CPU or a GPU and you just compile it over. So our compiler will take your code and compile it. It will run on the FPGA board. But as you can see from the first implementation, and just to be clear, their target was 100 milliseconds, which is what their processor base of this algorithm was producing. So just taking processor code and mapping it over gave them 5,000 milliseconds, so 5 seconds an image to classify. And at this point, which is what will happen to all developers as you start using FPGAs, they went to a panic attack and said, we spent all this money on an FPGA board, what'd you guys sell me? So the reason why their code was 5,000 milliseconds is it was optimized for a processor architecture. It was using a lot of small data transfers. It wasn't bringing enough data into the FPGA fabric for compute. So the accelerator was starving. So what we walked them through, and I'll show in the next example, is a couple of different optimizations that restructures our code in a way that optimizes usage of the FPGA fabric. So it is more explicit about memory management. It's more explicit about the parallelism you want to get. As of today, the compiler tools from Xilinx require you to change your code so that it expresses the type of functionality you want to use. Our compiler will optimize for the fabric based on the logic you have created in your code, but we will not add any logic that's not explicitly in your code. And that's going to become more clear in the next example. So in terms of where they started and where they wanted to get, with a CPU, they were at 100 milliseconds. It was a profitable application. First run of putting this on an FPGA and seeing, okay, turn the crank, accelerate it. They went from 100 milliseconds to 5 seconds an image. Completely useless example from their viewpoint. But after a week of optimization, they got down to 29 milliseconds, which allowed them to service more customer threads per server than they were serving before. And in terms of power consumption, if we normalize to the CPU, this solution is only consuming 14 watts to give them 3x the performance. So with an FPGA, you can get lower power consumption for your algorithm or for your accelerator and lower latency. One of the traditional bottlenecks of programming in this kind of device is that these results were achievable with 6 months of effort under a traditional FPGA design flow. So you took your software algorithm, you gave it to your FPGA design expert, and he'd say, leave me alone, and in 6 months, come back. And if you're lucky, maybe in 4 months, he had an initial version, but realistically, 6 months is when you'll get a result. With this compiler toolchain, you can get the same kind of results within 2 to 3 weeks because we're automating the tedious part of FPGA design. Where do you put registers? Where do you put connections? Which units you want to use? Which actual FPGA fabric you want to use and what clock frequency? So all of that is automated by the compiler, which allows you to play with your code and figure out what is the architecture you want to define. The other reason this took them about 3 weeks in this first example, is programming an FPGA with this environment, even though it's Opencl, requires a slight mind shift from what you're used to with a GPU or CPU. With this toolchain and with an FPGA, you're no longer trying to fit your algorithm into a fixed size box and breaking your algorithm every which way to make it fit into the box. Here, the box, as long as you bought a sandbox that's big enough, fits your algorithm. And this allows you to explore different ways of using your algorithm or chaining functions that can result in higher performance and lower throughput. So I'm going to walk through an example of how to get this done for a simple medium filter application, where the whole goal of the algorithm is to take this noisy image and smooth out all the noise so that you can then do classification or do more analysis on this image. So the basic algorithm is written here. It's a 3x3 window where you're computing the center pixel or the center value based on all the 9 surrounding neighbors. Now, one of the characteristics of the algorithm is that it has a lot of data reuse. So if you structure your code correctly, you do not have to go out to main memory all the time to fetch this data. This is where the embedded memories inside of the FPGA fabric give you a lot of freedom and flexibility as to what you can do. And it also reduces the power consumption. But, you know, your first start of code may be something you got from a friend, downloaded off the internet. It just runs on a CPU. It's functionally correct. This code will work on the FPGA, and it will compile through a toolchain. And you can run it. You can run it on Nimbix. It will work. That I guarantee. Now, what I don't guarantee out of this code is that it will be at any performance point that you'll be interested in. The main reason for this comes out of our profiling tools that analyze your performance on the board. So for this application, and I'm trying to get to a 1080p image at 60 frames a second, so 6 milliseconds a frame. First thing I get out of my profiler that's running in hardware is that it's taking 400 milliseconds a frame to process, which is troubling, but it's not the main problem with this code yet. Main problem with this code is how it's using memory. So if I look at the transactions that were recorded both on the read and the write, I am processing a 1080p size image, and I'm producing a 1080p size image, so I expect the reads and writes should be balanced or be similar. In this case, I see that I have 128 writes for the output image, but I have 147,000 reads. So I'm spending all my time going out to main memory. And the reason I'm doing that is because in my code, I have that I'm creating that 3x3 window out of this memory called input. And input is stored in main memory on the FPGA card. So in this case, FPGAs do not have a cache. If you want a cache or you want that kind of behavior in your code has to express it. So for this algorithm, we're going out to the main memory on the FPGA card constantly. So every value you want to compute is 9 reads. And if I look at my profiler trace, I can see that while my accelerator seems to be running all the time, it gets some data, there's nothing, it gets some data, there's nothing. So every time there's a blank, the accelerator is just sitting there waiting. So you have this great piece of hardware you built. It could go much faster. It can't because it has no data. So that becomes one of the main bottlenecks in FPGA design. How do you get data to feed the hardware that you created? So the way to change this is to recode your algorithm in terms of how it manages external memory. So you have to add some local buffering as part of your code, and you have to add the logic that will read out of those main memory into your local buffers, as well as recode your algorithm to work out of the local buffering. So this kind of behavior, while it's functionally equivalent to what you had in the first version, it can alter what your algorithm is doing. You can alter your results. So at the end of this code, you're getting the same image out, you're getting the same code out, but how you should actually bring this data in, what are the lines that you want to grab, what is the resources you want to use, depends on the algorithm. So the tool will analyze your algorithm for functionality and optimize away any code it can from the functionality expressed, but it cannot analyze intent. So today our toolchain cannot analyze this and say, oh, this is really, you want to cache. And based on your code, I should cache 3 lines of input image. It can't do that. It will just do a straightforward implementation of this algorithm. So as a designer, you are required to change your code so that you express the type of data reuse you want in your algorithm. Now, once you express this reuse, the hardware you're creating, you can think of it as you have your FPGA, your memory attached to the FPGA board. You have your FPGA device, and you have three blocks that were created out of logic, as well as some memory buffers that were created inside of the fabric for you. Now, when you bring in those local buffers, you're filling the buffers one at a time because you have one channel to memory. But when you're computing, since all of this memory is inside of the FPGA fabric, you can read it all in parallel. You can read all those memory channels at the same time. So those 9 pixels that you were reading out of memory one at a time, you're now reading out of a local storage 9 at a time. Then you store to a local result, and while you're starting to bring more data in, you can stream it out leisurely. It can overlap with the next line. So the result of this code transformation is that you went from 400 milliseconds down to 100 milliseconds of execution. So it's starting to get better, still not good enough, but it's already in the right sense in that your reads and writes to memory are about the same. It's balanced. You're seeing that your performance bottleneck, as shown by both our textual output and our trace view, seems much more compact. It seems that probably this is not the area where you need to focus on anymore. It's no longer the biggest bottleneck in your code. So, but it's still slow. So how do I make this actually go faster? So as we saw in the previous presentation or before lunch, some compilers require pragmas or attributes. Our compiler does the same. So you need to tell us that you want this hardware to run as fast as possible. And the reason why you have to express this as a designer is that running this computational loop as fast as possible consumes resources. So by default, our compiler is trying to be very stingy on resources so that you can cram in more functionality into the device, which means we will by default build the slowest piece of logic that will be functionally correct and will consume the smallest number of resources so you can add more functionality. Wanting this to go faster will consume more resources. So, it's the same as if you're building a house and you just tell us, build me a house. We're like, okay, you get a 1-bedroom house. If you want a 5-bedroom house, you have to, put your credit card down and say you want a 5-bedroom house. This is basically the same thing. You're telling us to go ahead and burn FPGA resources to give you the best performance possible. So what this will do is what we call pipelining. And the process of pipelining is, if I look at the default behavior of this loop, is I'm running computation for 1 pixel to completion, then the next pixel, then the next pixel, and so forth. I am using the least number of resources. I'm not overlapping any pixels, even though they could be, because they're in parallel. And I'm also not overlapping any of the color channels. So I'm reusing the same filter for every channel. I'm reusing the same filter for every pixel. This will be very efficient in terms of resources. It will be very slow. By pipelining, you're telling me that, you know what, use as many resources as you can so that you're only bounded by your memory access, and you're computing as many pixels in parallel as possible. So by the time this pipeline is full, or this processing element is full, at the same time I'm producing results for pixel 0, I'm computing 1, and I'm already fetching the data for 2. So this change completely altered the architecture that was implemented on the FPGA, but did not require you to change your algorithm. So if you move from the Vertex 7 card we have on Nimbix to the Kintix Ultra Scale cards we also have on Nimbix, it's going to be the same code. You're going to have to do the same transformations, the same type of memory arrangement, but you're not going to have to re-optimize your code because we changed the card. You're going to get the benefit of more resources or better performance because of the device, but your code will remain the same. The compiler takes care of the differences between devices. So now that we've asked the compiler to burn resources to give me more performance, I'm at the point where my memory didn't change, because that's what I needed to change in my code, was memory access. And my execution time is now 6 milliseconds. So I am within the boundary of my performance target. My algorithm is fixed, and it's done. And what would have been several months of trial and error in RTL design or hardware design became one code transformation to fix my memory access and one compiler flag. And the algorithm is done. So in terms of how you can get started with FPGAs, we have FPGA boards available on the Nimbix cloud, as well as our SCXL compiler tools, because even though I've been telling you all the goodness about our toolchain, until you try it yourself on the workloads you care about, it doesn't mean anything. So as a thank you for coming here to the summit, we have set up this email, Xilinx eval at nimbix.net, where every participant today will get 40 hours for free to try out both the compiler toolchain and executing your workload on the FPGA board. We also have application examples on GitHub that are ready to get you going and get you started in different domains, and I'll show them in a minute. So let me just show that real quick. So in terms of the examples, we have examples for acceleration, simple getting started, as well as security and vision. One thing in our acceleration examples that I want to highlight is we have a nearest neighbor linear search that's used in lots of graph algorithms, and we have a Bitcoin miner that we've downloaded off the internet. So as long as your code expresses the functionality you want, we do a lot of optimizations by default that will try to speed up your code as long as it doesn't increase your resources by more than a factor of 2. And we also try to eliminate all your code. So this Bitcoin miner, which is currently running 3 times faster than it does on the CPU, has no directives, has no pragmas, has no changes from our side. All we've done is set the makefile to target the SCXL compiler toolchain and target the board that's available on Nimbix. So out of the box, even though I did mention that you will get bad performance against optimized code, against regular CPU code, it might be just fine. So you do have to try it out. And even if it's bad, the tools will give you the insight you need to be able to figure out where your bottlenecks are. And the bottlenecks on FPGA design through our toolchain are always through how you use memory. And then adding that pipelining attribute takes care of 80% of your performance bottleneck. The last 20% is the interesting part, where you need to look at your algorithm and make sure that it's working as efficiently as it could. So think we should go through some questions before the demo, or what do you prefer?
So so you wanted to know if there's any questions before you do the demo?
Yes.
If anyone wants to ask now, or you want to see the demo first, it's up to you. If you have a question, raise your hand, and I'll. We have one.
So once you write your code and you want to know how long it's going to take on the FPGA, is there a deterministic way to determine how long it's going to take? What kind of speed up you'll get? Does the emulator work deterministically?
So the emulator is cycle accurate, and it's thread accurate to the logic that you're creating.
Okay.
So it will give you the right number of speed up. Now, one thing to keep in mind is that when you're emulating hardware and it's running on a cycle accurate mode, it will take exponentially longer than just running the code on the CPU. So it will take, the amount of time that simulation will run depends on your data set. So just to put it in perspective, doing 10 frames of HD video in emulation mode will take all day to run, whereas on the board it will take, less than a second.
All right, we'll go ahead with the demo, and then we'll break for questions after that.
Okay. So in terms of what we have available today on Nimbix, so we have two environments that we call the desktop and the runtime. So the desktop environment is where we have the SDXL toolchain installed. It's fully based on Eclipse, so you can use Eclipse knowledge to do your code debug editing. We do support GDB-based debugging of your code, all the way through the kernels that are going to be on your FPGA fabric. As far as debugging, besides breakpoints in GDB, you can also use printf statements if you want, and your accelerator will send you back hello messages if that's what you put in your kernel code. One thing to keep in mind with all the debug functionality is that the performance impact will be similar to what you get on a GPU or CPU. So if you're printf every single variable inside of your kernel code, it will kill your performance, because that data has to come back to the processor somehow. The Xilinx runtime environment is where we have the cards hosted right now. It's a batch mode execution. So once you've compiled your application, you can launch a batch mode job to get it to run on the card and get your results back. So in terms of the environment, and I'll just briefly go over it. This is for the SHA-1 hashing function example I talked about earlier. This is a lot of bit rotations, XORs, and gates, a lot of bitwise manipulation, which FPGAs are really good at, and processors are not, and GPUs are horrible at because of all the branching conditions. So inside of this environment, you can bring up the Eclipse GUI, you can use makefiles, whatever is your most comfortable programming environment. We've enabled it through SDXL. And then you can also run it in batch mode, and here I've pre-run it for sake of time. So once you pre-run your application, it executes the same as any shell application on the processor, where the parameters it's taken is your host code executable, what is the binary container you want to load onto that FPGA, as well as designation of the FPGA. So you can support more than one FPGA on your application. You can have multiple binary containers per application. So your reconfiguration times are about 200 milliseconds. And how many times you do that depends on your workload and the latency that you're trying to achieve. So it depends on what you want to do. It may be good enough that within one binary, you put in all the logic you want in hardware for your application, or you may need more than one binary. That's completely up to you. And FPGA 0 here is just a parameter. But in terms of processing and running on the board for a 512-bit block size of SHA-1, this gives you about 5 gigabits per second of throughput. The same implementation on an Intel processor with their hardened block gives you 400 megabits per second. And with that, I'll open it up to questions.
All right. Any Yes.
What do you say? How often are you finding that you sort of fit complete binaries in a single FPGA versus partitioning it into multiple binaries and reconfiguring? What do you see as kind of the trend there?
Excellent question. So for encryption, decryption workloads or hashing functions such as this, the whole workload will fit into one FPGA. For the video encoder, transcoder kind of operations, if I want to hit 60 frames a second, I need to partition it among multiple FPGAs. If I can live with lower performance, say 30 frames a second, then the whole application will fit on one FPGA. So performance is directly proportional to resources on the FPGA fabric. So it's very dependent on what is your target performance, how many FPGAs you'll need, or how many reconfiguration events you will need.
Who's next? Yes.
So is the NAE creation process, is that all relatively the same?
It's the same. We're using Jarvis. It's the same APIs. It's the same everything. The only difference is that some of these machines have the FPGA card installed.
Okay.
Anyone else? Going once? Oh.
Does this tool tell you how efficiently I'm using your FPGA?
So yes, as part of the estimation flow, we will tell you if it will fit or not fit, and what is the percentage of resources that you're using for your algorithm. And if it doesn't fit, what is the area where it's heavily over-consuming resources? So you can look at your algorithm and figure out if it's doing the right thing or not.
What version of Opencl do you support?
So we currently are conformant on Opencl 1.0, but we do have the pipe feature from Opencl 2.0. So you can do streaming between kernels inside of the FPGA fabric. And we're supporting, in future releases, we're supporting extending that stream concept or that pipe concept out to the I/O. So you can have live Ethernet traffic into the FPGA fabric, do your processing, and then send it back out without involving the processor. Yeah, so today we have two main library partners in ArrayFire and Ovis Systems. They're both specializing on machine learning libraries. So they're looking at CUDA-DNN functionality as well as OpenCV. And we are starting to expand our ecosystem to look into BLAS and more of the basic math functions.
Anyone else? All right. Fernando, thank you very much.